There's 1 minute left. Oh yeah, I don't. Yeah, I've heard that the lunch is different. What's that? Sure, why not? Yeah, we can.
What's going on? People going really good.
All right, guys. Before we start, first thing is that first announcement that we have 2 more lecturers who just arrived. So that's Tom, and Chris Tom back there. Okay. And Tom is actually the only medicine geologist. So watch out what you say. And the second thing, I heard there is a pool on when it might arrive. How can I join that? All right. So this morning we have 2 lectures by Andre. So go easy on him. He has 2 lectures.
So we're going to say something about lunch.
Oh, I think Tom is going to do that.
Very good. So we'll be surprised. Okay. All right. So the last thing we did yesterday was just to derive this very simple 2-flavor oscillation formula, which actually we can get a lot of mileage out of that. So just to remind you, this is what we said. You know, the probability that you're born as an electron neutrino and you're detected as an electron neutrino is given by 1 minus sine squared of 2 theta sine squared of delta m squared L over 4e. And it turns out that this is what we need in order to explain almost all of these neutrino data that we talked about on Friday. So just to give you a very, very quick feel of what, this is a completely trivial expression, but it's a very important one. As Maxime showed you last week, this shows up in these axion experiments. It shows up on neutron, anti-neutron oscillations for people who care about, say, baryon number violation. And so this is a very useful expression to have a lot of intuition for. Clearly, this is an oscillatory formula. It oscillates as a function of L over E. And by the way, if you never thought about this, you knew from the beginning that whatever expression you were going to get, it had to depend like L over E. Okay, and I'll let you think about that, but that just happens because of Lorentz invariance. So if you want, L over E is the proper time of the neutrino. And of course, it's proportional to the differences of the neutrino masses squared. So that means when you do an experiment and you have, say, you pick a value for L, and you have an energy that you can pick as well, this will tell you how much your flavor will change. And of course, the function looks like this as a function of L for fixed E. It's just a sinusoidal function. And there are 2 behaviors of this function which are very important. One is what happens when L is really small. And the other one is what happens when the oscillations are very fast. Okay, so in those two limits, life is very, very simple. So for example, when L is small, this just looks like 1 minus sine squared of 2 theta, and then a delta m squared L over 4e squared. So you get a certain behavior that turns on relatively slowly, so it kind of goes like L squared. That's one thing to keep in mind. And the other one is when the oscillations are fast, then the phenomenon that you get, you're mostly sensitive to just a mixing angle. Okay? Now, there are two physics types parameters that you can fit, so you can say that nature gets to pick what this mixing angle here is, and it also gets to pick what these mass square differences are, and this tells you what sort of experiment you're supposed to do. So the mixing angle, this is a sine squared of 2 theta, some number between 0 and 1. Okay, if this number is large, that means that the effects that you're looking for are going to be very large. If this number is very small, that means that you're looking for a very small effect. The other number is delta m squared. It kind of tells you what value of L and E you have to pick in order to get a significant result. And if you put back the engineering dimensions, this expression here gives you a feel for what kind of an oscillation length we're talking about in terms of neutrinos. And one number to keep in mind is if you have a 1 GeV neutrino, and if the neutrino mass square difference had been 1 electron volt squared, the oscillation length would be measured in kilometers. So you'd have an oscillation length which is about 1 kilometer, which is very, very long. This is kind of interesting. It sort of explains, in many quotes, why we didn't get to see this in the first types of neutrino experiments that we built. Because the distance that we were traversing was small enough that we were living over here. So we never got to see that any of this was going on, regardless of how big your mixing angle was. Okay? Now, it turns out, just so that, I will show you those numbers in just a second. It turns out that the typical mass square differences that we've measured, they are of the order of, say, 10 to the minus 3 or 10 to the minus 4 electron volts squared, which means that for a 1 GeV neutrino, if you want to see a 1 GeV neutrino oscillate a lot, you basically need baselines of about, say, 100 to 1,000 to 10,000 kilometers. Okay? And this leads to ridiculous experiments where you really have a neutrino source and you have to be incredibly far away. On the other hand, it's kind of nice that the Earth has the right size so that you can see this with the atmospheric neutrinos. And this is what we're going to talk about now. Okay, so this is the expression that you have, and that's what it looks like. And this is just to give you a feel for when do you get to see these effects and when you don't get to see these effects. So these plots are very, very common, which is why I'm showing you. This is a function of sine squared of 2 theta. This is a delta m squared measured in electron volts squared. And basically, in this red line over here, your probability is, in quotes, the same. And this is the behavior that I was telling you about. This is when delta m squared is very small. So your probability goes like a delta m squared squared. And over here, this is where your oscillation is very, very fast, which means you don't get to see the oscillation. You only see the averaged out oscillations. So you're mostly sensitive to the mixing angle. Okay, by the way, this is the result of an old experiment that didn't see anything. So because they didn't see anything, they could rule out some region of the parameter space.
In the case where L is very large or delta m squared is very large.
Correct, yeah.
So 2 average over 0, basically.
Oh, that's a good question. This is sine squared. So the sine squared function averages out to a half.
Right.
The reason this sounds a little bit surprising is that we massage the expressions in such a way that they look like sine squared. If you go back a couple of steps in the expressions that we derived, it's easier to see that the interference term goes away. That one goes to 0. But you're still left with some non-trivial flavor change, which is this effect that looks like that. Okay, good. Okay, so let's now try to explain how this fits some of the data that we talked about before. And I want to skip that. So this is the atmospheric data. This is the one that I showed you. It's the super K data that's very impressive. And again, there are lots of things that we would like to explain with this formula here. Okay? So first of all, if you look at this part of the data, this tells you about what's happening to the electron neutrinos. And remember, the solid black line, that's the expectation from your theoretical calculation of the flux. And you notice that the data and the black line work really well. Okay? So that means that the electron neutrinos aren't doing anything. Now, you can argue that the agreement is not particularly good between the data and the lines. So mostly what people do is that they will appreciate the fact that we're not very good at calculating this, especially the overall normalization of the flux. So normally when they fit the data, they will say, we think we understand the angular distribution of that calculation very well. We don't understand the normalization very well. So when they make a fit to the data, they allow the normalization to float, which is why the dotted line is a little bit shifted up with respect to the solid line. Okay, and there's a couple more details that we don't want to talk about. So again, the electron neutrinos work out fine. So we're going to leave them alone. But we know that the muon neutrinos don't work out very well. So we're going to try to use oscillations to explain that. And let's pick one of these panels. Everybody's favorite panel is this one. Okay, these are muon neutrinos that have relatively high energies, say about a GeV or so. So the idea is you look at this plot, and you notice that for neutrinos coming from above, your model works very well. Okay? And for neutrinos coming all the way from the other side of the Earth, the model doesn't work very well at all. Okay, so how do we use this oscillation formula that's on the board, and it's also up here, to explain these data over here? Okay? And it's pretty simple. So we want to pick a delta m squared such that for neutrinos coming from above, and those neutrinos travel about, 50 kilometers or so. So that's not very much. So we want the oscillation effects to not happen. So the way that I do that is I pick a delta m squared where if I plug in L equals 50 kilometers for an energy of about a GeV, the oscillation effect is really tiny. So that's one. So that explains these data over here. On the other hand, I go to the other side of the Earth, and I want to see this very, very large oscillation effect. It's a 50% effect. Half of my new mu's are missing. So what I do is I pick the delta m squared in such a way that the oscillations are very fast. Okay, when I say that the oscillations are very fast, it has to be compared to something. And it's usually compared with resolutions of your detector, for example. In this case, there are two important resolutions you have to care about. One is the fact that you don't know how long the neutrino has traveled very well. Now, why is that? Because, of course, you don't get to see a neutrino ever. All you see is that the neutrino hit something and produced a muon, and you can see that that muon is going in some direction. So I have to use that information, the muon direction, to reconstruct where the neutrino is coming from. And I can do that fairly well, but I can't do it perfectly, as you can imagine. I mean, there's some, the muon and the neutrino are not perfectly aligned. There's some angle that the muon comes out with. So that gives you some uncertainty on knowing which direction the neutrino is coming from. That means when you're doing a calculation of this, you're not really measuring this function. You're measuring this function here integrated over a bin of L or a bin of theta. And if the oscillations are very fast inside of that bin, then this averages out to a half. The other possibility, of course, is that measuring the neutrino energy is also equally hard. Because again, you don't get to see the neutrino. You just see that a muon has come out with some energy. If you knew the angle, by the way, reconstructing the energy would work quite well. But you don't get to see the angle because you don't know where the neutrino is coming from. So there is some uncertainty there as well. So you have to average over that. And here the averaging is really big. They have what's called their low energy sample and their high energy sample. So they basically break up their neutrino species into the high energy ones and the low energy ones, and they have to integrate over what they anticipate the distribution of neutrinos are as a function of energy. Okay? So that means I have to pick a delta m squared such that the oscillations average out for neutrinos coming from the other side of the Earth. And that means that the probability looks like this, which I wrote down on the board. And if I want to get this factor of 2 effect over here, I pick sine squared of 2 theta to be 1, which is as big as it can be. And now I have already used up a lot of my parameters. The only other exciting thing that happens is that the behavior changes between short distance and large distance. So that the place or the region where that happens tells you what the delta m squared will be. So I picked the delta m squared in such a way that this transition occurs for a cosine of theta of around 0. And these are a horizon arriving neutrinos, sort of. And that tells me what the delta m squared is. Okay? So I can explain this panel here in my data set with neutrino oscillations. And in the process of doing that, I figure out that the sine squared of 2 theta is about 1. And I figure out that the delta m squared turns out to be about 10 to the minus 3 electron volts squared. What's really exciting is once you've done that, you've exhausted all of your physics parameters. So that means that all the other panels have to be fit by the same choices that you've made. And that's what the dashed lines indicate, and it works ridiculously well. Okay, so for example, for the low energy neutrinos, this is how this works out. And you see that you start having oscillation effects even for things that come from above. And these are higher energy neutrinos. You still have oscillation effects, but they're not as strong. And this is for really, really high energy neutrinos. And you don't see much of an oscillation effect because those neutrinos have very high energies. And remember, your oscillation length scales with the energy. So the higher the energy, the longer the oscillation length. So for ridiculously high energies, oscillations don't have time to turn on, even on the Earth. Okay, so this is an incredibly successful story that measures parameters really well. Just to convince you, we've repeated this experiment in beam experiments as well. So we've done experiments in Japan, and we've done experiments in the US to confirm this phenomenon with a neutrino beam. What's nice is once you know the delta m squared, you know what kind of a distance you need. So again, for a 1 GeV neutrino, you need distances of, say, 500 to 1,000 kilometers. So we've done those experiments, and we see these really big effects because the mixing angle is very, very large. Yeah?
Are we assuming 2 generations?
Yes, we are. So I'll talk about 3 generations in just a second. That's a very important point. Remember, I said early on, the electron neutrinos weren't doing anything. So we kind of left them alone. So that means that whatever oscillation is going on, it's interpreted to be oscillations between nu mu's and nu taus. There's an interesting question you can ask, which is, so if it is oscillation between nu mu and nu tau, how do I convince myself of that? So how do I confirm that experimentally? And people have done experiments to try to do this. This is the opera experiment that's happening at CERN. And also the Super K experiment itself has tried to do measurements where they try to see the tau neutrinos as well. Now, seeing tau neutrinos is very, very hard. Seeing tau neutrinos in Super K is really hard because that's not an experiment that's designed to see taus. But on the other hand, you can see neutral current events at some level, so they have some sensitivity to pions, so they can make these measurements of the pions. And I'll just see this very briefly because it's kind of interesting. And it is something that we haven't done very well yet. So basically, when a neutrino comes in, these are pretty high energy. They will hit something, and they can either have a charge current reaction or they can have a neutral current reaction. A neutral current reaction for high enough energies is a pretty messy event. So a neutrino comes in, hits something, and breaks up a nucleus, produces a bunch of pions. And you can see some of that in your Super Kamiokande experiment. Now, these are very dirty events, and they don't look anything like the nu mu events or the nu e events that they're very good at. So they have a sample of events which they know or they classify as neutral current events. Now, if you have an oscillation from a nu mu to a nu tau, the nu taus, first of all, still participate in the neutral current events just like everybody else. So that means that your neutral current sample is not expected to change from the neutral current part of the scattering. But on top of that, if you have enough energy to produce a tau, more often than not, the tau will decay hadronically into pions, and that will look like a neutral current event, sort of. Actually, a lot. In these detectors, a lot like a neutral current event. So by studying this neutral current sample, you can ask yourself if you have some excesses there. And Super K has done that. And they get an excess at around the 3 sigma level. So they have, in quotes, seen the tau neutrinos by studying their neutral current sample. Okay, and that's a pretty robust result, but it's a really difficult result. And I don't think you would claim discovery of tau neutrino oscillations that way. So the Opera experiment is very similar to the experiment that I talked about earlier, this donut experiment, where you actually try to see the tau track in a neutrino beam. And I'm trying to remember how many events they have now. Does anybody know? I think it's like 7 or 6 or 9. So they have a significant number of events now, and they have they now claim evidence for this new mu to nu tau oscillations. Okay, and the experiment has stopped taking data. I wish I remember these things better, but yeah, the experiment has stopped taking data, and that's their main goal, was to observe this tau appearance. Okay, so that's what's happening there. Now, before I move on, I have to mention very quickly what are called matter effects. And I will do this on the board. So first of all, the really important message is that we have seen this expression in action for the survival probability of mu neutrinos in the case of the atmospheric neutrinos. Now, there's one exciting thing that happens to neutrinos, which is what happens when they propagate in matter. And when they propagate in matter, it turns out the oscillations change. Okay, so I will just tell you very briefly what the idea is, and I will give you a little bit of consequences of that. And we can probably talk about this more in the discussion. So let's look at the Lagrangian for neutrinos when we include the weak interactions. Okay, so the neutrinos have a Lagrangian, and that Lagrangian will include a term that comes from the W exchange. Okay, so let's just write down that term. And let's write this down in a model where I've integrated out the W boson. And this is a term where you have the W exchange of a neutrino scattering on electrons. Okay, so that's a current interaction. And I can do a fierce rearrangement of that in such a way that this looks like this is my neutrino current, and then there's an electron current as well. And it's a left-left interaction, right? So it's a V minus A interaction. So this term here belongs in my Lagrangian. So the question then is, if I take this interaction into account, and I want to write down the equation of motion for a one neutrino state in the presence of an electron background, okay? So let's say I want to do that. So this is what's happening in my Lagrangian at the field theory level. I know how to write down the one neutrino state. So the one neutrino state is the A dagger that lives inside of this field. And then I can write down the equation of motion for that. But instead of doing this in the vacuum, which is normally the calculation that we perform, let's do this in an environment where you have electrons. And let's say I have electrons at rest. That means that I have to calculate this quantity here. Okay, so this is the expectation value of this operator in a background that has a lot of electrons in it. Now, this turns out to be very easy to calculate because this is a gamma mu electron. If you remember, this will look like E dagger E with some up to some numerical coefficient. And if you remember, E dagger E, that's the electron number operator. So this here counts the density of electrons that I have. Okay, so that means that this object here, in a background that has electrons in it, this is proportional to the number density of electrons. Now I want to do a little bit better than that. I want to do this calculation in the rest frame of this electron gas. And I want the electron gas to be at 0 temperature. So these are just electrons at rest. So if these are electrons at rest, this is actually not the entire number density of electrons that you have, but it's only half of it. Because if you want, this is the left-handed number of electrons. There's also the right-handed number of electrons, and I'm not sensitive to those. And since this is a gas at rest that's not polarized, I get a factor of 2. Okay? And of course, this is a current operator, but the only part of this that I see is the energy density, which is proportional to the number of particles that I have. The other component of this current here would have to do with the velocity of my electrons. But my electrons are not moving, so that part is 0. So that means I get a term that looks like that. Okay? So does everybody see that? So this means, if you remember, there's also the neutrino kinetic energy term. Which is something that's proportional to this. And if you remember, my Dirac equation comes from this piece of the Hamiltonian, of the Lagrangian here. So now I'm adding to my Lagrangian another term that looks a lot like that one. It's also proportional to gamma mu, but it's now multiplied by this average number density of electrons. So this means if you ask, what's the equation of motion for my neutrino in the presence of a gas like that, it'll be, and let me get the factors of I right. There's an I here. It'll be something like that. It'll be some I del slash minus. How do I write that? Oh, sorry. So what this means is, in the presence of this electron background, my neutrino Dirac equation gets modified. So here's the standard kinetic energy piece, which is this del slash piece. But then I get this other term, which is only in the gamma 0 direction, if you want to think about it that way. And it's proportional to the density of electrons in the medium. So this is a very exciting effect. It looks a lot like sometimes a finite temperature effects for people who like finite temperature field theory. And the other thing it does is, of course, it breaks Lorentz invariance. And that's not a big surprise because you're doing your calculation in a particular reference frame where the electrons are at rest. And what this does then is that the solutions to your equation of motion will not be the standard plane wave solutions anymore. They will be some modified plane wave solutions where the dispersion relation gets modified. So instead of having that the energy is proportional to the momentum, which would be the case if the neutrino mass had been 0, and I'm neglecting the mass for now, you get this extra contribution that changes your dispersion relation. Okay? So the idea then is that your dispersion relation is modified if the neutrinos are propagating in a medium. And again, the physics that's simplest and most related to this is a refraction of light when light is propagating through a medium. As you know, as a electromagnetic wave changes from one medium to the other, the dispersion relation changes, which is to say the velocity changes. It's no longer the speed of light. So the exact same thing is happening to these neutrinos here. Okay? And this is all we need to know. Yeah? So the question is there a contribution from neutral current interactions? The answer is yes. We don't write that one down because the effect that we're interested in is the oscillation effect. Now, what's happening is this is a modification to the dispersion relation of the neutrino. So that changes your oscillation equation because the oscillation equation is all about the fact that neutrino number 1 and neutrino number 2 have different dispersion relations because the masses are different. This here is also saying that the electron neutrino has a dispersion relation that's different from the dispersion relation for the muon and the tau neutrino. The neutral current effect also changes things, but it does that in a democratic way. So it affects the muon, the tau, and the electron neutrinos in exactly the same way. So even though the dispersion relations have changed, they all change in the same way, and the oscillations don't care about that. So for the same reason that the oscillation formula only care about the mass square differences of the neutrinos, it doesn't care about the neutral current piece either. Okay? That's very important. Okay? So this is the most important part. The last comment, which is very easy to see, but I'm not going to derive it here, is that the same thing happens for anti-neutrinos. So if you calculate the dispersion relation for anti-neutrinos, the exact same thing happens, except that you get a sign, which is a minus sign instead of a plus sign. Now, what's one way of remembering this? This is coming from this weak current over here. And this weak current happens to be a vector current. Okay, vector minus axial vector, but still a vector current. And if you remember, electromagnetism is also a vector current. And as you remember, if you add the a mu the a mu piece to the electron dispersion relation, you will note right away from the equation of motion itself that the electron has negative charge and the positron has positive charge. That comes out of just calculating the equation of motion. So that plus and minus charge for matter versus antimatter is encoded in the fact that you have a vector interaction. As you probably remember, when you have a scalar interaction, the particle and the antiparticle all interact with the same sign. So there's no repulsion versus attraction. And the same is true for a spin-2 interaction. A spin-2 interaction is always attractive. And we're very familiar with that one. Okay? So this is what happens. And then for our purposes, basically what this does is that it changes the way in which we calculate neutrino oscillations. Okay? And the simplest way to do that is what's done over here very quickly, is that you can describe this neutrino oscillations using a Schrödinger equation. So you can convert the neutrino oscillations into differential equations that look like this for the neutrino mass eigenstates, right? This is what we talked about before. These are eigenstates of the Hamiltonian. So that means that their propagation is governed by an equation like this. I can combine these two equations into a two-level quantum mechanics problem. And then I can re-express the system in the flavor bases, in the nu e, nu mu bases. So you get a differential equation that looks like this. And if you solve this differential equation, you get the oscillation formula that we worked out on Friday. Okay? So this is nice because now I can add to this by taking this charge current effect into account. So the charge current effect changes the dispersion relation of the electron neutrino relative to the one for the muon neutrino in this way. So now your Hamiltonian looks like that. Okay? And the number people like to calculate is this number A, which is called the matter potential. It's called the potential because if you interpret this as a two-dimensional quantum mechanics problem, it looks exactly like a potential. It does what a potential does. The other way of thinking about this is that it changes your energy relative to the momentum. So it has this feel of a potential energy. Okay, and that's why we'll look at it that way. So now, if the neutrinos are propagating through matter, life is different, and you have to take these effects into account. And the question then is, can we solve neutrino oscillations in the presence of matter? And the answer is, first of all, yes, because this is a two-level non-relativistic quantum mechanics system. We're all at least graduate students, so we all should know how to solve that. And if you don't know how to solve that, you have to pretend you remember how to do it. But it could be a very complicated problem. Because this matter potential here, that tells you what the density of electrons is in the medium, and that number can change as a function of position. So this is kind of like having a time-dependent non-relativistic quantum mechanics problem. So you probably remember that's the part that you talk about towards the very end of the course, where you're too tired to learn anything anymore. But that's sort of the problem that you have to solve. So there are lots of different ways of solving this. Now, fortunately, in many cases, the matter potential is a constant, in which case it's totally trivial to solve this problem. This is just a two-level system, and all you have to do is to calculate the eigenvalues and the eigenvectors of your Hamiltonian, and then you just solve the quantum mechanics problem. Okay? So for us, I'm not going to do that on the board because it's very boring and it takes time. All that we care about is, for example, the oscillation expression from, say, nu e to nu mu in the two-level system now looks exactly like the vacuum expression, except that you have a modified oscillation frequency, and you have a modified mixing angle. Okay? And there's a lot of information hiding here that we can take advantage of, which is, for example, your modified mixing frequency depends on your matter potential, but it also depends on the plus or minus sign between the matter potential and the delta m squared, which is one thing that people find exciting. And the other thing that happens is, of course, your mixing angle also changes. And people have explored this formula a lot, and I'll talk about one context in which this is very important for us right now. Not right now, but right now and in today. Okay? So this is the main idea. If you're propagating through constant matter, that's what happens. Your mixing angle changes, and your oscillation frequency also changes. And that gives you some opportunities to measure certain things. Back in the day, a long time ago, people got very excited by the fact, for example, that if you pick the right value of the matter potential, even if your mixing angle was very small, you could have an effective mixing angle that was very large. So people got excited about that. Now, the last thing, which I won't talk about, but people can ask me in the discussion, is that if you want to try to understand the solar neutrino problem, it turns out that matter effects are really important. Okay, it didn't have to be that way, but nature chose it to be that way, that matter effects are very important. And it's actually matter effects in the sun. Okay, so the sun is pretty dense, especially inside. And if you look at matter effects, they're very, very important for solar neutrinos. And on top of all of that, the matter density in the sun changes a lot. So again, if you're a neutrino that's born inside of the sun, and you're making your way out, you're born in a very dense medium, and you propagate out to a very, very non-dense medium, right? A very rarefied medium, if you want to think about it that way. And I don't know how much you have a picture of the sun, but the density of the sun decays more or less exponentially. So it's pretty dense in the medium, in the middle, and of course, once you exit the sun, there's nothing more, there's nothing left, so the density goes to zero. So you have this environment where it turns out that the fact that your electron number density is changing very rapidly is very important. Okay, so it's kind of frustrating that this two-flavor oscillation picture does not explain neutrinos coming from the sun very well, and constant matter effects don't explain it very well either. So you have to do this slightly more complicated analysis, which I will not do, but we can talk about it in the discussion. It's actually a very nice picture. It's pretty easy, but I don't want to spend a lot of time talking about that. Okay? So this is the idea, but I will say that, on the other hand, two-flavor oscillations explains the solar neutrino problem really well. Okay? So it gives us some hints about what the delta m squared is. So this is the stuff that we can talk about in the discussion. But I do want to mention a different experiment where the vacuum formula works really well, and that's one of these gigantic achievements of understanding neutrino oscillations. So again, to summarize, two-flavor oscillations explain the solar neutrino puzzle quite well. And if you do the calculation right, you learn what the delta m squared is supposed to be. And the delta m squared turns out to be about 10 to the minus 5 or 10 to the minus 4 electron volts squared. So this means, and the mixing angle is large. This means you have another delta m squared that explains how electron neutrinos disappear, okay, with a large mixing angle. And you have to ask yourself, can I do an experiment to test that? And remember, if your delta m squared is 10 to the minus 4 electron volts squared, for a 1 GeV neutrino, your oscillation length is 10,000 kilometers. 10,000 kilometers is very long. Okay? So that's the point that we have to start and worry about that. So people had the idea of doing an experiment with reactor neutrinos. Reactor neutrinos have energies of about 5 MeV. And this is how we discovered neutrinos to begin with. So these are good experiments that we know how to do really well. So if you're aiming at a delta M squared, which is about 10 to the minus 5 electron volts squared, this is what's written over here, and you have energies of about 5 MeV, you need a baseline of about 100 kilometers to see an effect. So this means you need to do an experiment with a nuclear reactor, and you have to put your detector 100 kilometers away. Now, I haven't emphasized this enough, but nuclear reactors are very good neutrino sources, but they're really crappy at pointing at your detector. Okay? That means that they send neutrinos everywhere. By the way, any neutrino experiment is kind of like that. We're really bad at pointing neutrinos anywhere. So the farther away you go, the fewer neutrinos you have. So going 100 kilometers away is a challenge. But people were very, very smart, and they noticed how Japan works. And so this will be a very simplified description of Japan. So here's Japan to zeroth order. And as has become less funny recently, Japan gets a lot of energy from nuclear power that you probably know. They have a lot of nuclear power plants. A lot of them were shut down recently, and they're turning back on again because they figured out that they really need the nuclear power plants. And what happens is nuclear power plants use water for cooling. Japan is an island, so if you put your nuclear power plant close to the ocean, you have access to a lot of water for cooling. So there's a bunch of nuclear power plants everywhere in Japan over here. So somebody noticed, hey, if I build a detector here, it's about 100 kilometers away from a bunch of nuclear power plants. That statement is correct. It's oversimplified. You actually build it like over here, but it doesn't matter. So that's the idea. So you build a really large detector that is about 100 kilometers away from a lot of nuclear power plants. And remember, 100 kilometers is very far, so you need as many neutrinos as you can in order just to get a signal. So you need a very big detector that happens to be about 100 kilometers away from all of your different nuclear reactors. And then you do the experiment, and then you see what happens to your neutrinos. And remember, if you pick, what's exciting about what you're looking for is that you kind of know the delta M squared already from the solar neutrino puzzle, and you know the mixing angle is large. So the kind of effect that you're looking for is not a subtle effect. It's a really big effect. So as long as you have enough statistics and you give the neutrinos enough time to oscillate, you should see something. And this is this really impressive plot that's over here. So what they do is they calculate how many neutrinos they should see, and then they look at how many neutrinos they actually see. They divide those two numbers out. And then, of course, there are neutrinos coming from everywhere. So you can calculate the average L over E for those neutrinos. So it's an average that depends on the fact that you have all these different power plants. So you have to weigh them with different L's and so on. So you get some L effective over E. And of course, the neutrinos that come from the nuclear reactor have a spectrum. So that's why you get a different values of L over E. Okay? So this is the plot that they get. And this is by far, until very recently, this is the prettiest oscillation plot we've ever made with data. Okay? It's a really impressive plot. First of all, it tells you that the probability is not 1, but it's way less than 1. Like I said, it's a big effect if you go far away enough. You notice that their error bars are small enough that you can claim that you've seen something. And even more importantly, they get this really amazing oscillation curve. Okay, so this is the Kamlin experiment in Japan. It's a very big liquid scintillator detector close to where the Super K experiment is, or it's in the place where the old Kamlin experiment used to be. And it can be explained ridiculously well with this two-flavor formula as well. Okay, so we're very, very sure that this is happening, and it works incredibly well. And of course, it agrees very well with the information that you get out of the solar neutrino data as well. And again, this is what's shown over here. Okay, so this is the stuff that we can explain very well with the solar neutrino data. And this is what we can explain very well with the two-flavor mixing hypothesis. So basically, the picture that we've constructed, and I'll draw it over here, is pretty simple. So first of all, two-flavor oscillations works quite well. And I'll try to explain why that's the case. So we have 1 delta m squared, which is about 10 to the minus 3 electron volts squared. We call this one the atmospheric delta m squared. We have another delta m squared, which we call the solar delta m squared. That's about 10 to the minus 4 electron volts squared. And this is part of the information that we've gotten. We explain the oscillation of the atmospheric neutrinos by nu mu to nu tau oscillations. And we need a large mixing angle. We explain the oscillations of, say, these Kamlin neutrinos as nu e oscillating into either nu mu or nu tau. We don't know which, because this is a low energy experiment. The energies are about 5 MeV. And if you're a 5 MeV neutrino and you hit something, you have no hope of ever producing a muon or a tau because you don't have enough energy. So that means that from the point of view of the experiment, if you turn into a nu tau or a nu mu, that neutrino is just lost to you. You never get to see it. Okay? So this is explained that way. And the mixing is also large. And the question then becomes, now this is clearly not the whole picture, because I know I have 3 neutrinos, so I can't, these are these toy fits to data, but how do I make this into a coherent picture that explains everything? And the idea is, yeah.
So if you don't have enough energy to produce muon tau, how do you identify that?
So that's a very good question. So from the Kamlin experiment, we don't know if this is a muon or a tau neutrino or something completely different. From the solar neutrino experiments, including the snow experiment that I talked about on Friday, you know that the nu e's are changing into nu mu and nu tau because of the neutral current measurement. And because the Kamlin phenomenon is very, very similar, or it seems to be the same physics that's explaining the solar neutrinos, that's why we're confident in saying that. Okay? So any more questions? So the question you're allowed to ask is, so why does this picture work so well, even though we have 3 neutrinos? And the answer is the following. Remember, the way you want to picture this is that you have a 2-frequency phenomenon. Or there are 2 oscillation lengths every time that you have neutrino oscillations. One is long and the other one is short. Okay, so the short oscillation length is this atmospheric one, and the long one is the solar one. And this ratio here is about a factor of 30. Okay, that means that one oscillation length is about 30 times longer than the other. So even though you have the nu e going to nu mu and nu tau from the solar picture, that doesn't screw up the atmospheric picture very much, because the atmospheric picture is such that you don't get to see these solar oscillations. The wavelength of that is too long. Okay, and that's why the 2-flavor approximation works very well for the atmospheric neutrinos. Okay? For the solar neutrinos, you're allowed to ask, how come the electron neutrinos don't get to see this other oscillation length here? Okay, that's a fair question to ask, because if they could see that, if you did an electron neutrino experiment, you should see this other oscillation length, which is actually much shorter than that one, so that one should appear more. So the reason you don't get to see that is, again, if you are in a regime where delta m squared solar is too small, that means you don't see those oscillations. That would mean that the electron neutrinos would still oscillate with some frequency that looks like this, but it will be proportional to some other mixing angle that we haven't measured yet. So the fact that in this gross picture here, you don't get to see the electron neutrinos participating in oscillations proportional to this frequency here is because there's a mixing angle that's small. Okay? So that's what we had figured out until about, say, 10 years ago. So we were pretty sure that this picture worked very well. We knew why the two-flavor approximation was a great approximation, because there's a hierarchy of oscillation frequencies. So if you could see the fastest one or the shortest one, that's the one you would see first. And it turned out that the electron neutrinos didn't get to see the fast oscillation because the amplitude for them to see that was small. So the next challenge in neutrino physics was, so how do I get to see this effect? Or can I get to see electron neutrinos participating in phenomena that are proportional to this oscillation frequency? Okay, so this was the big question in neutrino physics 10 years ago. And we came up with lots of different ways of doing that. The coolest way is to do a reactor neutrino experiment as well. And we did 3 of those because we wanted to be very, very sure. We were looking for a potentially tiny effect because, again, we're always at the mercy of what nature picks for these numbers. So if nature picks a really small number, you don't get to see anything. And we knew that that number was already reasonably small. So we did another batch of atmospheric experiment or reactor experiments, which is here. And the idea is, again, the following. I know the delta m squared very well. It's 2.5 times 10 to the minus 3 if you put in the numbers. That means if I make a reactor neutrino experiment with a baseline of about 1 kilometer, then I get a really big effect. Except that I don't know what the amplitude of the effect is. Okay? So I can maximize my effect by building an experiment at the right place, and then I have to hope and pray that the mixing angle is not too small. So if you do that, it turns out that the effect that people were sensitive to was about a few percent effect. In this case, it turned out to be bigger than they anticipated. It turned out to be an 8% effect. But they constructed experiments that were sensitive at the percent level. Now the question is, how do you do this? And what you want to keep in mind is that to zeroth order, these reactor neutrino experiments are a disappearance experiment. That means that you start out with some neutrinos, and you end up with fewer neutrinos on the other end. In order for that question to make sense, you have to know how many neutrinos you have to begin with. And that's what makes these experiments hard. So if you have a reactor, and you want to ask how many neutrinos are coming out from that reactor, if you've never thought about this, this turns out to be a very difficult problem to do in practice. Okay? So first of all, there are lots of things you can ask. The most obvious one is, if I have a nuclear reactor, where are the neutrinos coming from? What's the physics process? It's mostly beta decay. So that's good. This is a nuclear reactor. It's burning these heavy nuclei. And these are all beta decay processes. They emit a lot of neutrinos. Now, we know beta decay pretty well. But the question then becomes, how well do we know the beta decay of everything that's in the nuclear reactor? And if you never thought about this, what's in the fuel of the nuclear reactor is very, very messy. And it changes as a function of time, obviously. It's combinations of uranium and plutonium and all of the daughters and granddaughters and great-granddaughters of all of these decays. So you have to understand your fuel composition quite well. You have to understand how it changes with time. You have to know the spectra of all these beta decay quite well. And you have to do this in an environment that's very, very difficult to make measurements. So knowing the flux of neutrinos coming from a nuclear reactor is really hard. You get some information, like you get the power output of the nuclear reactors. That's what the power companies care about a lot, because that's how they make money. So they monitor the power output of the nuclear reactors quite well. It would be nice to be able to measure other stuff. There's some political challenges. If you go to a nuclear power plant and you ask them, can I place a very large detector next to your nuclear reactor? They usually don't like that. We've done lots of measurements with what are called the research reactors. These are reactors that have simplified or fuel which is easier to understand, in many quotes. And people have done beta measurements of that. And then that helps a lot. And we've done a lot of research in these, a lot of measurements with these research reactors. the step from that to a real reactor is very complicated. So the way you do this experiment is that you don't want to rely on the calculation of the flux, but what you do is you do what's called a two-detector experiment, right? So your nuclear power plant is here. These things, by the way, I think are the cooling towers. They're not where the nuclear reactor is. But you put a detector over here, and then you put another one over here. You make those detectors the same, whatever that means. And then by making a measurement over here, you can predict how many neutrinos you're supposed to get out there. That's the idea. The real discussion was, how do I make sure that you have two detectors which are exactly the same? And when you mean exactly the same, these are big tanks of liquid scintillator. You have to ask silly questions like, did I put the same amount of liquid scintillator here and there? And you're supposed to say, sure, you do that. That's pretty easy. I know how to do that. I do that in the kitchen all the time. So the question always is, how well do you have to do that? And you have to do it really well. And these things are filled in by, the truckload. So keeping track of all of that is very challenging. But this is what this experiment is about. This is data from the Gouvea experiment. And this is their near detectors. They have a whole bunch of near detectors. This is their far detectors. They're making a measurement of how many neutrinos they expect, divided by, how many neutrinos they see, divided by how many neutrinos they expect. And you see that this is what they see in the near sites. This is what they see in the far sites. This red curve is a one-parameter fit, because you know the delta m squared really well. So that number is fixed. So the only thing you can play with is the sine squared of 2 theta. So you get a sine squared of 2 theta of about 0.08 or so, and that fits these data here quite well. So that means you've learned that there's a third mixing angle in the picture. So you can have the new e's disappear, let's put it that way, with a small mixing angle as well. Okay, and this explains lots of things. It explains why the two systems separate in a way that makes life easy for you to interpret the data, because you have a hierarchical you have hierarchical frequencies. That's very important. That means that most of the time you only get to see this frequency because this one doesn't have time to turn on. And when it comes to electron-like events, one of the mixing angles is small. Yes?
So how does that differ to the case above where you have tau?
I will show you that in just a, yeah. So the question is how does this work out? Yeah. And I think the way you want to see this, and I'll show you some more expressions. The idea is, of course, everything now is a two-frequency phenomenon. And when you're talking about the new e's disappearing, the oscillation probability looks like 1. That means if L is equal to 0, they don't disappear. Then there are going to be different terms in your expression. There will be one term that's proportional to the long wavelength, and that one comes along with a large coefficient. Then there's another term which is proportional to the short wavelength, and that one comes about with a small coefficient. That's the idea. Okay? So this is what we've been able to do. And this is sort of where we are today. We've actually done a little bit better. The other thing we've seen is that we have seen nu mu oscillating into nu e with the same small mixing angle. This one is the same as that one. In an experiment where the baseline is short enough that you don't get to see this wavelength here. Okay, so this is a confirmation of the fact that this phenomenon does happen with a small mixing. Okay, and this is actually, these are the experiments that are taking data now. This is the NOVA experiment at Fermilab and the T2K experiment going on in Japan. And they have both measured what's called a theta 1-3, and I'll show you what those angles mean in just a second. Okay? So is everybody happy with that? So if we put everything together, I'm sorry? Oh, good. So these are, I think it's experimental hall 1, 2, and 3. So by the way, the Diabe experiment is in China, very, very close to Hong Kong. And it's a reactor experiment in an area that has lots of nuclear reactors. So they have 2 clusters of nuclear reactors. So they have nuclear reactors here and here, let's say. So they built near detectors over here, and then they built the far detectors over here. So that's the general idea. That's the right experimental setup.
What's the simplified version of China?
Oh, China is much easier than Japan, right? So this is China. This is a way better approximation for China, I think. So the experiments are like here. But we don't care because this is very small. This is about 1 kilometer. And Hong Kong is around here somewhere, to 0th order.
So here the multiple points correspond to different measurements?
That's correct, yeah. So they have 2 halls where they have detectors. And those are at slightly different average baseline from the cores of your nuclear reactors. And that's how you get these all of these points. And so let me say this again. Every point is a detector. So that means that in this experimental hall 1, there are 2 detectors for this measurement. In this hall, there's 1 detector. And in this hall, there were 3 detectors at slightly different positions. And they actually have more detectors that they were still turning on at the time when they made this measurement. And like I said, there's something called the Reno experiment that's in South Korea. It has a result that's very consistent with that one, with almost the same error bar. It's a little bit worse. And then there's something called the double show experiment in France, in the north of France. And they are not as sensitive, but they've also seen this effect as well. And you can see from this plot that the best fit value for sine squared 2 theta turns out to be 0.08. This story was a very exciting story because at one point, everything we knew was that this number, sine squared of 2 theta, was less than about, 0.15 or so. That had been the best experiment we had done before. So if you're planning the next experiment, you normally try to be sensitive to an order of magnitude smaller effect. So all of these guys built experiments that were sensitive at the 1% level. So they were very happily surprised when the very tiny effect that they were looking for turned out to be not very tiny at all. This was a very large effect, in quotes, and that the people who had done the experiment before had gotten really unlucky, that they were off just by a factor of 2. If they had been a factor of 2 better, they would have started to see some effect of this.
Can I ask one question?
Yes?
So how do you break the degeneracy between, let's say, small delta m squared and large mixing, and then large delta m squared and this?
So the question is, how do you distinguish large delta m squared and small mixing from a large delta m squared and small mixing? If you're in the regime where your oscillation looks like this, you cannot do it. So that means if you're in the small L regime, then small mixing and large delta m squared is completely degenerate with the other way around, with large mixing and small delta m squared. However, once you get to do an experiment that's close to the oscillation length, that's when you get to see the oscillation happening. So you don't get confused between the mixing angle and the wavelength. So the atmospheric neutrinos are a great example of that. The place where you measure the delta m squared is basically from this factor of 1/2, while the place where you see the delta m squared comes from the place where you change from one regime to another. So the information is coming from orthogonal places, which is why it's often very important to be able to do an experiment where you can see the oscillation. So if you can see the oscillation in some way, then you sort of disentangle the amplitude effect from the phase effect. Okay, and if you don't have that, then life becomes a little bit harder. So this is what I just wrote down there. So more questions? Yes? Okay. Okay. That's a very good question. So by the time this plot was made, the answer was no. So basically, in order for you to make this plot, you used as an input the fact that you knew the delta M squared from the other experiments. Now, if you look at more recent Diabay data, they actually have sensitivity to the delta M squared themselves, because again, just like the Kamlin experiment can see this distorted spectrum, they can also see a distorted spectrum. And the reason they didn't have it in this paper, this is the 2012 paper. So the theta 1,3 was discovered the same year the Higgs was discovered. They didn't have enough statistics to do that measurement. Also, it's not just statistics, but you have to analyze the data carefully to make sure that you understand the shapes of things well enough so that you can claim that you have a distorted shape. That's a little bit trickier as far as an analysis is concerned. And now that they've done this measurement quite well, especially they can do measurements in the near detector, they've even found some interesting features in the shapes of the flux of neutrinos from nuclear reactors that people don't understand yet. Nonetheless, the effect that they see from the oscillation is distinct enough that you can determine what's going on. Okay? All right. So let's look at what the picture really looks like. And it looks like this. So again, you have that nu e, nu mu, and nu tau are linear combinations of nu1, nu2, and nu3. Okay? So that's the picture. There's a unitary mixing angle, mixing matrix over here. And we'll talk about this after the coffee break. But in order to properly parameterize this matrix, you need 3 angles and a phase, just like the CKM matrix. So let's stick to that because that's stuff that you know. And there's a wrinkle here, but we'll talk about that in just a second, or after the break. So I have this matrix, and this is how the mixing angles are defined. So theta 1,3 is UE3. Theta 1,2 squared is the ratio between these 2 entries over here. And theta 2,3 is the ratio between those 2 entries over there. Yeah. It does not. The only thing that changes is that you have more free parameters. So there are 2 extra CP phases that you can add. But you can't see those with neutrino oscillations. You have to do different kinds of experiments. So that's why you can use your intuition for the CKM matrix for that. This is often called a PDG parameterization because that's what the PDG uses. There's a fun thing to think about, which is, so we know what nu e, nu mu, and nu tau mean. We also know that nu1, nu2, and nu3 are neutrinos with a well-defined mass. There's a fun question, which is, so which one is which? Right? So that's a physics question. And if I say that neutrino number 1 is the neutrino that has mass m1, that doesn't solve the problem unless you know what m1 is as a number. Since you don't know that, we have to come up with some naming scheme for nu1, nu2, and nu3, or a way that makes them distinct. And we do this in a weird way. So I have to explain that. So our definition is the following. We say that neutrino number 1, which has mass m1, is lighter than neutrino number 2. That's step 1 of the definition. Step 2 of the definition is that neutrino number 3 is either heavier than 1 and 2 or lighter than 1 and 2 in such a way that the magnitude of delta m squared 3,2 and 3,1 is bigger than the magnitude of delta m squared 1,2. Okay? That's the definition. And unfortunately, that's the definition we're stuck with. And there's a reason for that. If we picked a more sane definition, like M1 is the smallest one, M2 is the second smallest one, and M3 is the heaviest one, that would have made sense, right? But the reason we don't pick that is because if we had chosen that, there would be ambiguity in interpreting what the entries of the mixing matrix mean when you try to map them into these experiments that we've made. Okay, yeah. So very good question. So what happens if 2 of them are the same? If 2 of them are the same, then some of the mixing angles are unphysical. Because what happens, the way you want to think about this is if 2 masses are the same, you can perform a rotation in that subspace of the mass matrix, and then nothing changes. So that allows you to dial off one of the mixing angles and the CP phase. Yes? That's correct. Yeah, that's what we'll talk about next. So basically, there's this phase factor here, and the question is, we've measured those three mixing angles. We haven't measured this potential phase factor there. And the only way we could have measured that is if all the masses had been different, which they are, and if theta 1, 3 had been non-zero. Again, if one of the mixing angles vanishes, then you lose this CP odd parameter as well. Okay? So this is the picture. So we have this definition, and what happens is, with this definition of M1, M2, and M3, the sign, plus minus sign of delta M squared 1, 3 is physical. It's either a positive number or a negative number, and that's a question you can ask. On the other hand, the difference between, the sign of M2 squared minus M1 squared is defined to be positive. So you can't ask if that's a positive number or a negative number. That's not a physics question. Okay? But the way we parameterize things, the sign of delta M squared 3, 1 is a physics question. So with this picture, which is a very simple picture, it parallels the quark picture as much as possible. We can ask, what haven't we determined yet? And so these are the measurements we've made. So I always like to point out that these are really impressive measurements. And I guess for this kind of audience, I can tell you that when you were born, none of these parameters existed, let alone we had not measured any of them. Okay? So these are brand new parameters. They have existed for less than 20 years. And in that span of time, we've actually gotten to measure them really well, sometimes at the few percent level. This theta 1, 3 mixing angle, which is the last one that we measured, is known quite well. So sine squared theta 1, 3 is about this big. So it's about a 4% measurement, okay, which is really impressive. Ironically, sine squared theta 2, 3, that's the atmospheric mixing angle. That's the one we saw first unambiguously, and that's the one that has the biggest error bar. Really, really big error bar, more than 10%. Okay? And the frequencies, the delta M squares, we've measured quite well. They live over here. Okay? So this is where we are. And I'm sorry that I'm using the slide so much, but I think it helps talk about these things more quickly. So here's what we don't know. The most exciting thing we don't know is what's called the neutrino mass ordering. So there's a side. So you can ask yourself, if you know that there are three masses, and you know that there are two mass square differences, you can ask yourself, how many different ways can I combine the three masses in order to reproduce this picture of the mass square differences? And it turns out that there are two ways of doing that. One is this way on the left, where you have M1 less than M2 less than M3. And then there's the way on the right, which is M3 a lot less than M1 less than M2. Okay? And these are two qualitatively different pictures. And what's exciting is the fact that we don't know which one is correct. Okay, so why don't we know which one is correct? The reason is pretty simple, is that we've never done an experiment where you get to see both frequencies at the same time. You either see one of them or you see the other one. And like I said, when you do these solar experiments, you're mostly measuring this frequency here because you're not sensitive to this very, very tiny amount of electron neutrino in the state number 3. So you only get to see this frequency here. So you don't care if it lives up here or down here. The physics is the same. When you're doing the atmospheric type experiments, you only get to see this frequency here, but your resolution is poor enough that you don't get to see that these two levels are split. As far as that experiment is concerned, those two guys fuse into one level. You don't get to see that because the wavelength associated to that is too long. Okay? So one question we don't know then is this thing called the mass hierarchy. People have started moving away from the word hierarchy towards ordering. Yes? That's a good question. That's a definition. So I define M2 squared to be bigger than M1 squared. And I can do, as long as I stick to the definition, I can do that. You can ask yourself, what would I have gained if I had not stuck to that definition and I had allowed those numbers to also fluctuate? You could have done that. It would have modified a particular interpretation of one of the mixing angles. And we would not want that. That would just lead to confusion. By the way, there's another way that people like to define the mass eigenstates. By the way, I didn't tell you what these colors mean. So this bar here represents the flavor composition of the mass states. So the fraction of the bar that's colored red, for example, is the probability that a neutrino number 1 is measured as an electron neutrino. That's also known as UE1 squared. Okay, the entry in the matrix squared. So these colors, so this state here has a lot of electron neutrino in it. This one has only a little bit. And again, the same as this one has a lot of electron neutrino in it. This one has only a little bit. So it turns out that there's another way of defining the mass states by their electron composition. So neutrino number 1 has the most electron in it. Neutrino number 2 has the second most electron in it. And neutrino number 3 has the fewest amount of electron in it. And you can also define things that way. And that would have been unambiguous as well. And in the process of doing that, you would have found out that M2 is bigger than M1 experimentally. So instead of defining it, you can just measure it. Yeah. Yes?
So compared to the most state-of-art procedure we have now, how much work the both tied together?
So the question is, how much precision do we need to see those two oscillations at the same time? The answer is it depends what you want to see. So for example, if you look at the atmospheric neutrino experiments, they can see, in quotes, the solar delta m squared, the long wavelength delta m squared, a little bit. So if you have a large statistics atmospheric neutrino sample, you should be able to see these solar effects in the atmospheric neutrino sample. Now, that's not very exciting. What we really would like to see is we don't just want to see the two delta m squares in action at the same time. What we really want to see is interference. Because this is a three-flavor system, you have the possibility of having interference between one oscillation regime with the other oscillation regime. And in order to do that, you need an experiment that's qualitatively better than the experiments that are running now, which is why we're in the process of designing these much bigger experiments, both in the United States and in Japan, which are aimed exactly at seeing effects which are proportional to the interference term. So more questions? Okay, yes?
On the previous slide, it seemed that measure the total CP. Is that the CP violating phase?
That's the CP violating phase.
Okay, so
We don't measure it very well.
oh yeah, I see that.
Yeah, so at the 3 sigma level, it's between 0 and 360 degrees. And we're still in the phase of the timeline where we're very, very sensitive to small fluctuations in one experiment and the other.
But the 1 sigma level, is that full range with leptogenesis?
Oh, that's a very, very different question. We can talk about that in the discussion. The answer is we don't know what leptogenesis has, as far as this parameter is concerned. Okay? So let me just finish talking about this picture, and then we can get a short break. But so again, we don't know this thing about the mass ordering, which is how the masses are ordered, and that's sometimes referred to as the neutrino mass hierarchy. And this one here is called the normal ordering, or the normal hierarchy, and this one here is called the inverted hierarchy. This is called normal because this looks more like what all the other fermions do. This one here is different from this one, so we had to come up with some other name. So we call it inverted. The other questions we don't know is whether CP invariance is violated, which is this delta question. The other thing we don't know, which is a funny question, but flavor physics people care about this sometimes, is that if you look at these pictures here, and you look at the green and blue bars, you will notice that the way that I drew them, the green and blue bars are the same everywhere. They have the same amounts. And that's a logical possibility, according to the data. But we don't know if that's true or not. So for example, if we look at neutrino number 3, we can ask, is it more blue than green or the other way around? We don't know the answer to that. Now you can ask yourself, why does anybody care what the answer to that is? We know it's pretty big, and some people care about this. So if you're in the business of trying to understand where mixing comes from, that's one of those things you can try to predict. Okay, and by the way, I'll say this in just a second. There's a really fun thing about the neutrino sector is that the mixings are all really large. So one thing that you want to train yourself, especially when you talk to non-particle physics people, is that there's no neutrino that looks like, none of the mass eigenstates look like any of the flavor states. Not even a little bit. Okay? Neutrino number 1 is a very healthy mixture. This one is a very healthy mixture of nu e, nu mu, and nu tau. Neutrino number 2 is a very democratic mixture of nu e, nu mu, and nu tau. Actually, people who build flavor models get really excited about the fact that this looks like, a third, a third, a third. And if it really looked exactly like that, it might mean something, maybe. Okay? And again, the same thing goes for neutrino number 3. If you neglect this theta 1,3 effect, this is like a 50-50 mixture of nu mu and nu tau. So again, there's very, very little alignment between the flavor states and the mass states. They're very, very different. Okay, so this is something to keep in mind. And of course, what I want to say is the next generation of neutrino experiments has, as a side effect to its physics plan, they would like to understand the answer to these questions over here. And most importantly, I think the main question that we're asking is, can we design experiments that are capable of testing non-trivially that this picture is actually correct? And we've not gotten there yet. We know that this picture works really well, but you can ask yourself, are we missing something? Is something that doesn't belong to this picture here present and we just haven't seen it yet? Okay, so we should probably take a break and then we'll continue talking about this.